All right, so today we're going to try something a little bit different.
Oh.
Yeah. So instead of just like, diving into a book and like summarizing it,
Hmm.
we're going to imagine like, what if we had to explain this to like the smartest person, like a total genius?
Ah, I see. So it's not about dumbing it down.
Right.
It's about finding like the most elegant way to get to the heart of it.
Yeah, exactly.
Yeah.
Like the most crystalline path to understanding. And the funny thing is, I think that actually connects really well with the book we're looking at today, Understanding Analysis.
Oh, interesting. How so?
Well, this book, it's not like your typical calculus textbook.
Right.
It really digs deep into the why behind the what.
I see.
Like it's trying to lay bare the DNA of math,
Hmm.
and do it in a way that even a genius would appreciate.
I like that analogy. It's about revealing those hidden structures.
Exactly. And the real number system. That's like our case study for this deep dive.
Makes sense. It's where so much of higher math really begins.
Right. And the book, it really emphasizes this idea that it's not just about verifying stuff we already know. It's
Mm-mm.
about those moments where our intuition like totally fails us.
Right, where the familiar rules break down and we have to re-examine our assumptions.
Exactly. And that's where the real breakthroughs happen. At least that's what I got from the book.
Yeah, and that's what makes analysis so fascinating. It's like we're pushing the boundaries of what we can even conceive of.
So right out of the gate, the book is like, rigor is key.
Okay, and it points out how a lot of introductory math courses, they kind of focus on these familiar calculus theorems,
Yeah.
like proving polynomials are continuous.
Right, which is important. But
Yeah, it kind of misses the point of why analysis was even developed in the first place.
so why was it?
Well, the real excitement came from trying to grapple with those areas where our everyday intuition just falls apart.
Give me an example.
Think about infinite series or those weird functions that are continuous everywhere, but you can't differentiate them anywhere. It's like, whoa.
Yeah, those are the real head scratchers. And the author, he's like totally against this whole, let's make it easier by just skipping the hard stuff.
Right, because that's like cutting out the heart of the subject, right?
Exactly. It's like you're cheating yourself out of the real beauty of it.
The goal should be to make those tough ideas understandable
Yes.
and to show why they're worth the struggle.
And that connects back to our whole genius thing, right?
Oh, absolutely.
Okay.
I mean, if you were explaining this to someone with a truly exceptional mind, you wouldn't shield them from the challenge. You'd present it in a way that highlights its profound significance.
Yeah, you'd want them to see the elegance, the depth.
Exactly.
All right, so to lay the groundwork, the book starts with something that seems pretty basic,
Okay.
proving that the square root of 2 is irrational.
Ah, yes. Theorem 1.1.1. It uses proof by contradiction, a classic.
Yeah. Can you walk us through that?
Sure. So we start by assuming the opposite of what you want to prove.
Which is that the square root of 2 is rational.
Exactly. So if it's rational, it can be written as a fraction, p over q, where p and q are integers and q isn't 0. And we assume this fraction is in its simplest form, meaning they don't share any common factors other than 1.
Got it. So far, so good.
Now, if pq equals 2, then p4 must equal 2q whole. This tells us that is even. And a key fact about integers is that if the square of an integer is even, the integer itself has got to be even too.
Right.
So we can write p as 2k, where k is another integer, substitute that back into our equation. We get 2k equals 2q.
Okay.
Simplify that a bit, we end up with 2k equals q.
Uh-huh. Now we see where this is going.
Right. Now q is even, which means q itself must also be even. But wait a minute.
We said P and Q have no common factors other than 1.
Exactly. That's our contradiction. Our initial assumption that the square root of 2 is rational must be false.
It's got to be irrational.
Boom! It's like we've stumbled upon a number that doesn't quite fit into our neat system of fractions. It's like finding a new color that doesn't exist on your color wheel.
That's a great way to put it. It's this realization that our tools, they're not always enough.
And it makes you wonder what other limitations are lurking out there.
Right. And this example really drives home a point about rational numbers.
You mean how they're not always enough for even something as basic as taking a square root?
Yeah, like the rationals, that's Q for anyone keeping score at home, they've got these gaps.
Gaps.
Yeah, even though they're dense like between any two rationals, you can always squeeze in another one.
Right.
They still don't form a complete continuous line.
It's like there are these tiny holes, these missing pieces.
And that's where this concept of a field comes in, which the book introduces.
Right. So Q is a field, but the integers z and the natural numbers n, they aren't.
So what's the deal with fields? What makes them special?
Well, a field is basically a set where addition and multiplication behave nicely.
Nicely.
Yeah, they're commutative. Like
Uh,
A plus B is the same as B plus A, same for multiplication.
okay.
Associative too. So A plus B plus C is the same as plus B plus C, and so on. And you've got the distributive property where a times B plus C equals A times B plus A times C.
Hmm.
And crucially, a field must have an additive identity, that's 0, and a multiplicative identity, which is 1.
Okay.
And every element needs an additive inverse, like negative A, and every non-zero element needs a multiplicative inverse, 1 over A.
So why don't integers and natural numbers fit the bill?
Well, think about the integers. Can you always find an integer that you can multiply by, say, 2 to get 1?
Nope, not unless it's 1 or a -1.
Exactly. So they don't have multiplicative inverses for every element. And for the natural numbers, it's even worse.
Yeah, they're missing both additive inverses and multiplicative inverses.
Right. You can't always subtract and stay within the natural numbers, and the same problem with division.
That makes sense.
Yeah.
So back to rational numbers being incomplete.
Yes, that incompleteness is a key reason why we need to go beyond Q.
But how do we really grasp that incompleteness?
Okay, so think about the square root of 2 again. We can make a sequence of rational numbers that get closer and closer to it, like 1.4, 1.41, 1.414, and so on.
I see where you're going with this.
Right. These are called Cauchy sequences, where the terms get arbitrarily close as you go further down the line.
So what's the problem?
The problem is that even though these sequences in Q seem to converge to something,
Yeah, they're getting closer and closer to the square root of 2.
that something, that limit, it's not actually part of Q.
Oh, I see. It's like they're reaching for something that's just out of reach.
Exactly. So Q has these sequences that are trying to converge, but their limits are outside the set. And this idea, it becomes super important when we finally define the real numbers.
It's like those sequences are pointing to something beyond what we can currently grasp with just rational numbers.
Exactly.
Okay, so to handle those missing limits, we need to move beyond Q. Right.
And to do that, we need to talk about sets.
Sets, like collections of stuff.
Yeah, exactly. Set notation gives us this precise way to talk about groups of mathematical objects.
Okay.
These collections, they become the building blocks for everything more complex.
I see.
We talk about unions of sets. That's all the elements from both sets combined.
Okay.
Intersection, what they have in common. And subsets, when one set is entirely inside another.
Right.
We can even define sets in different ways. Listing all the elements, describing them with words, or using a specific rule to say what belongs.
So it's like we're expanding our mathematical vocabulary before tackling this new number system.
Exactly. We need the right language to describe what we're building.
Okay, and once we've got the language, the book then goes into proof techniques.
Ah, yes. The art of proving things in math.
We already saw proof by contradiction with the square root of 2. What about direct proof?
Direct proof is more straightforward. You start with what you know,
The assumptions,
right? And then you use logic, step by step, to get to the conclusion.
like a clear chain of reasoning.
Exactly. And the book makes a funny point. It says that using an indirect proof, like contradiction, when a direct one is possible, is kind of like bad manners in math.
Like you're taking the scenic route when there's a perfectly good highway.
Uh-huh. Yeah. Something like that.
Right, and then there's mathematical induction.
Ah, induction. That one's super useful when we're working with natural numbers.
How does that one work?
Okay, so induction is like a domino effect.
Okay.
First, you gotta knock over the first domino. That's the base case. Show the statement's true for the first natural number, usually 1.
Mm-hmm.
Then you assume it's true for some arbitrary number, n, and show that this automatically means it's true for n plus 1.
So you're saying if it works for one domino, and if it working for any domino means it worked for the next one,
Yeah,
then they all fall down. Got it.
precisely. And the book has this nice example with a recursively defined sequence.
Ah, yes. It's x sub n plus 1 equals 1/2 times x sub n plus 1, starting with x sub 1 equals 1.
Right. They use induction to rigorously prove that this sequence is always increasing.
Okay, so they show that x sub 1 is less than or equal to x sub 2. That's the base case.
Yes. And then they show if you assume x sub n is less than or equal to x sub n plus 1, then it must also be true that x sub n plus 1 is less than or equal to x sub n plus 2.
So each domino knocks over the next, and we prove it for all natural numbers.
Ugh.
Pretty neat.
It's a very elegant way to prove statements about infinitely many things.
And I like how the book brings in a bit of philosophy, too. Kronecker's quote about natural numbers being the work of God,
Yeah, contrasting that with the more modern axiomatic set theory approach.
which is all about building everything up from these fundamental axioms.
Exactly. And the book makes a good point. It says that while these foundational questions are super interesting, we should focus on understanding the real number system first.
Get a good grasp of the building before we worry too much about the bedrock it's built on.
Precisely.
Okay, so we've seen the limitations of rational numbers, we've armed ourselves with set theory and proof techniques, and now
Now we're ready to fill those gaps in Q and strengthen our concept of number.
that leads us to the axiom of completeness.
This is a big one. It's the foundation of real analysis.
Okay, so what is it exactly?
Imagine you have a set of real numbers that's bounded above. That means there's some real number that's greater than or equal to everything in the set.
Okay.
The axiom of completeness says that this set must also have a least upper bound, also called the supremum.
Meaning there's a smallest number that's still bigger than everything in the set.
Exactly. Think of it like a fence. Your set can't go past the fence, and the supremum is the closest point to the fence that's still on the right side.
I like that visual. So we accept this axiom as true without needing a proof.
Right. It's one of those fundamental assumptions we make when constructing the real numbers.
And it doesn't hold if we're just dealing with rational numbers.
Nope. The book gives a great example to show why.
Lay it on me.
Consider the set S of all rational numbers whose square is less than 2. That's all the rationals are, where r squared is less than 2. This set is non-empty, 1 is in it, for example, and it's bounded above, 2 would be an upper bound.
Right, because nothing bigger than 2 can have a square less than 2.
Exactly. Now, if we're just in the world of rational numbers, does this set have a least upper bound that's also a rational number?
I'm sensing a trap here.
Think about it. We can find rational upper bounds for S, like 1.42, and then an even smaller one, like 1.415, and we can keep going.
Oh, I see. We can keep getting closer and closer to the square root of 2, but we can never actually reach it with just rational numbers.
Exactly. There's no smallest rational number that can serve as an upper bound for that set. It's like there's a hole where the square root of 2 should be.
But if we're dealing with real numbers,
Then the axiom of completeness swoops in to save the day. It guarantees that this least upper bound must exist.
and it turns out to be the square root of 2, which we already proved is irrational.
Right. So the axiom of completeness is essentially filling those gaps in the rational numbers. It's what makes the real number line truly complete.
So this axiom is pretty powerful. What are some of the things that follow from it?
Well, one important consequence is the nested interval property. This says that if you have a bunch of closed intervals, each nested inside the previous one,
Okay.
then there's at least one point that's in all of those intervals.
So no matter how much we zoom in, there's always something there. No holes.
Exactly. We also get the Archimedean property. This one says that no matter how big a real number you choose,
Okay.
you can always find a natural number bigger than it.
So even if we pick a ridiculously huge number, we can always find a bigger natural number.
You got it. And this has a cool consequence. For any two different real numbers, we can find a fraction 1 over n smaller than the difference between them.
And that helps us prove the density of rational numbers in the reals, right?
Theorem 1.4.3.
So even though we've got those irrational numbers filling the gaps, there's always a rational number lurking between any two reals. It's wild.
It might seem counterintuitive, but the rationals are indeed dense in the reals.
So now we've got to talk about cardinality, how we measure the size of infinite sets.
Ah, yes, cardinality. This one can really mess with your intuition.
Tell me about it. The book shows that the set of even natural numbers has the same cardinality as the set of all natural numbers. How is that even possible?
Well, we can pair them up perfectly. Each natural number n goes to a unique even number, 2n.
Okay, but shouldn't a part of something be smaller than the whole thing?
Not when we're dealing with infinity, and it gets even crazier.
Oh no, what now?
The set of all integers, including negatives and 0, it also has the same cardinality as the natural numbers.
How do we even begin to wrap our heads around that?
The book shows how we can list all the integers in a sequence. 0, -1, 1, -2, and so on.
I see. So even though there are more integers, we can still create a one-to-one correspondence with the natural numbers.
Exactly. They're both countably infinite.
But then we hit a major difference. The rationals are countable, but the reals are uncountable.
That's a huge distinction. The book sketches the idea of how to count the rationals, how to list them all out.
So you're saying we can create an infinitely long list of every single rational number?
In theory, yes. It's a clever way to organize them using these sets, A sub n, based on their numerators and denominators. But when we try to do the same thing with real numbers,
Breaks down.
it breaks down spectacularly. The proof uses this neat trick with nested intervals.
Okay, remind me what those are again.
They're a sequence of closed intervals, each snugly inside the one before it.
Right, like those Russian nesting dolls.
Exactly. So we assume, just for argument's sake, that we can list out all the real numbers.
Okay.
Then, using this supposed list and the nested interval property, we can construct a sequence of nested intervals, each one cleverly designed to exclude the next real number on our list.
So it's like we're systematically eliminating every real number on our supposed complete list.
Exactly. And then, bam! The nested interval property guarantees that there's still a point inside all those intervals, a point that wasn't on our list.
So our list wasn't complete after all.
Exactly. Which means our initial assumption that we could list all the real numbers was wrong.
So the real numbers are uncountable. There's just too many of them to even put in order.
And this also means that the set of irrational numbers, all those numbers that can't be expressed as fractions, they have to be uncountable too.
Wow. So most real numbers are actually irrational, even though we don't see them as much in our everyday math.
It's kind of mind-blowing when you think about it.
The book mentions that all this has a really interesting historical side to it.
Oh yeah, like how mathematicians like Cauchy, Bolzano, and Weierstrass were doing all this amazing work with real numbers before anyone really nailed down a rigorous definition.
It's like they were building these incredible structures without knowing exactly what they were standing on.
Exactly. They had this intuitive grasp, and they used it to make incredible progress. And then later on, folks like Weierstrass came along and formalized everything.
And the book ends chapter 1 with this really thought-provoking idea.
About how these mathematicians, by looking at infinity through the lens of finite things, like sequences,
Yeah.
they opened up a whole new world of mathematical exploration. It's like they invented a new telescope to peer into the vastness of the infinite.
So let's wrap up. What have we learned about this fundamental, foundational, real number system?
Well, it might seem straightforward at first, but it's built on a surprisingly deep foundation of definitions and that all-important axiom of completeness.
That one axiom that fills those gaps in the rationals and underpins all of real analysis. It's kind of amazing when you think about it.
Absolutely. And to all you listeners out there, think about this. Even though rational numbers are everywhere, they're actually less numerous than irrational numbers. What does that tell us about the nature of numbers in infinity?
That's something to ponder.
Yeah.
And finally, what questions are you now asking yourselves about the nature of numbers and the structure of space? What new mathematical territory do you want to explore now?
This deep dive into the foundations is just the beginning. There's a whole universe of mathematical wonders waiting to be discovered. So go out there and explore.
And keep that spirit of explaining to a genius in mind. It might just lead you to some fascinating insights.
Absolutely.
Until next time.
Happy exploring.